Okay, so next video in our line of topics is on torque and equilibrium. So now we're looking torque and equilibrium. So new concept altogether when we start talking about torque. And it really comes about, hopefully we get here. What is torque, okay? And we kind of talked about that in our preview video where we said that there's that engine and the engine wants to make something rotate. And really torque is then about the ability of getting something to rotate. Now, I picked a picture of a sailboat, and I don't know how many of you have ever been sailing before, but sailboats are always those things that, they've got this big, tall sails, okay, big, tall sails, and yet then there's this kind of point on the boat that we look at rotating, and it's almost like it wants to flip. Okay, so like if the wind starts to push on it here, or push on it here, or push on it here, we're applying force. And that force is what we're looking at as something that has the ability to make something rotate. So an applied force makes an object want to rotate. Now, the boat doesn't flip over, okay, all the time. I should say it has flipped, they flip over at times. But ideally what you see is you see all the guys, everybody on the boat goes over to here, and so they're really trying to distribute. So if I look at even a plane this way, it's like they're trying to put more force in this direction to try to keep it from balancing. There's another part to the boat that they don't talk about, and that part is called the keel, and the keel actually is underneath here. It's like that big fin-like thing that's underneath here. And that actually is using the force of the water to kind of keep it from rotating. So we have lots of different forces at play when we're doing various things, and we look at how things start to rotate. Okay. Now, I'm just going to break this down to even a kind of a simpler thing. So we've got our sailboat there, but it's a lot like maybe even looking at if I said this is a hinge and this is a door. Okay. So here's my little door handle, right? You ever wonder why they put the door handles on the far edge? Well, let's think about this a second. If I were to apply a force here, or I applied a force here, which force would be the bigger force? Okay, think about that a second. Which force would be the bigger force? And you might say, okay, if I push here, it's not too bad. It's like I can get away with a smaller force. But if I pushed here, I'd have to use a bigger force, okay? Bigger force. And the reason why is because you're closer to the point of rotation. Okay, so we say there's a distance that you are away from the point of rotation, and that force that you apply that's perpendicular to that surface, okay, is from perpendicular from the point of rotation, is how we get torque. See, torque is nothing more than the product, okay, product meaning multiplication, of your force times the distance. That's what torque is. It's a product of your force times your distance. Goes right back to what we talked about when we talked about levers and when we talked about simple machines. So all of that stuff plays a role when we start talking about torque and the rotation. Okay. Now, again, torque has a symbol. The symbol for torque is the Greek letter tau. Okay. And the torque is a force times a distance. But now this is the key thing here. It's the distance that's perpendicular to that force. We've seen force times distance already, okay? And that's how we calculated work. But work and torque are two different things because work was in the same direction and torque is in a perpendicular direction. So you have to be careful with it. Unit-wise, it's the same. It's a Newton meter. So torque is measured in Newton meters. Torque is also a vector. So when we start talking about it, direction is important. When we talk about direction in terms of rotation, we start to talk about things in terms of clockwise or counterclockwise. And I like to always just use clockwise or counterclockwise. I think some book sources will actually say counterclockwise is always positive and clockwise is always negative. That was probably reversed for you. But that's because we're looking at it in terms of a math problem. In the math, if you remember that quadrant, we went quadrants 1, 2, 3, 4. So that's how we kind of defined what positive was. So now back to my sailboat problem. If this is my point of rotation, these forces right here would cause the motion to go around a circle like that, where these forces would all cause the motion to go like that. And we start to create kind of a balance, and that's typically what we talk about when we get to the subject of equilibrium. Okay, just to make sure, lever arm, moment arm, this is called a lever arm, okay, or a moment arm. And the moment means about that rotation, okay, it's moment of rotation, not like moment as in an instant of time. Okay, so now how do we get to equilibrium? Okay, picture that I picked here is a bridge. We don't want bridges to fall down. We want bridges to stay up. Okay, it's an equilibrium standpoint. Now here's the trivia question. You can kind of look this up, but this is a famous bridge in Minnesota. Famous bridge in Minnesota. Now, we want our bridge to stand up. So essentially I'm going to take the point here and the point here, and I'm going to say there's a force that's applied on this section of the bridge. Okay, so I'm going to draw this way. The bridge looks like this, and then there's a pylon here and a pylon there, and these two pylons supply a force. That's an upward force that hold the bridge up. Now, why do we have to supply an upward force? Well, it's because the bridge itself has some mass to it. Okay? Now we start talking about this bridge. This bridge would have a mass, okay, of so many kilograms, which means that it would have some weight. Okay? Now we do look at these beams or these bridges and we say, is the bridge uniform or is it not uniform? Now that's a big thing, because if the bridge is uniform, that means that its center of gravity would be directly in the middle. If it was not uniform, then the center of gravity shifts to wherever there's more matter. Okay? Center of gravity relates back to the amount of matter that you have. Typically, we build bridges to be uniform. We don't build them like a baseball bat where you have heavy and light in. Okay? So in other words, we could put a point right here to represent the center of mass of our bridge, and we'd have then the weight of our bridge. Now, in an ideal situation, the amount of force going down is equal to the amount of force going up. So in other words, each of these pylons would have to support the weight of half of the bridge. Now that's great as long as we never ever drove on the bridge, okay? But what happens is we typically start to drive cars and trucks on the bridge, which creates an unbalance in these forces, I should say. It still keeps us in equilibrium, but now the bridges, or the force here and the force here, are no longer equal to each other. So let's say we actually put a car on our bridge, and our car has a weight as well. So this is now the weight of the car, this is of the bridge. So now, in a translational sense, okay, translational meaning going up and down, the up arrows have to hold up the down arrows. We want zero net force here. We want this to be equal. So my up arrows were F1 and F2. They have to be equal to the downward arrows of the weight of the car plus the weight of the bridge. Now, if we look at this, that's how we kind of equate translational, okay, forces. Now the bridge, on the other hand, can also have the ability to kind of start to rotate, okay? And so typically as a car's placed on there, it's almost like the bridge wants to start to flip, okay? And we start to look at this in terms of rotations. Now I'm going to switch colors here so we can talk about rotation in a different sense. If we were to examine the bridge, we can pick any point along the bridge to examine rotation about some of these forces, because again, it's about the torque of these forces. But because we want the torque to be equal to 0, it really doesn't matter where I pick it. So I usually try to pick it at a point that's lining up with one of my unknown forces. Okay? Because remember, do we want bridges to rotate? No. Okay. So in other words, if I pick this as a point of rotation, so I'll say point of rotation. Okay? The point of rotation would happen where I would have the car would cause me to have a clockwise rotation. The bridge itself would have a clockwise rotation. And then the force over here would happen to balance that all out. So I'd look at it in terms of the counterclockwise rotations. Now the only way I can figure out forces though is if I know distances. So I would need to know, say, the distance from here to here. And I would need to also know, say, the distance from here to here. And I would also need to know, say, the distance from here to here. Okay? So I would have to know distance for the car and distance to the center, and then the total distance of the bridge. So I'd have like a distance to the center, distance to the total, and actually distance of the center, isn't that just half of the distance total? So if I took the distance total and divided by 2, that would give me half. So in other words, I can look at this in terms of rotation. So my clockwise rotations would have to be equal to my counterclockwise rotations. My clockwise rotations would come from the FG of the car times the distance that car is sitting plus the FG of the bridge times the distance of that bridge, or half of the, because it's a uniform bridge, is got to be equal to my counterclockwise rotations, which is going to be my F2 times the distance of the bridge. Okay? And so this gives me a secondary equation that I can look at. So I get 2 equations when I start talking about equilibrium now. We have translational, that's the forces, and we have rotational, and that's the torques. Okay? So now let's put this to a little practical use. And I have here a sumo wrestler, and my sumo wrestler is on a scale. Okay, first of all, our sumo wrestler would exceed the capacity of our scale. That's the big thing here. So we have a scale that only has a maximum of 250, and we have to figure out how to weigh them. Okay, so we're going to use a plank or a board, and it's 3 meters long. It apparently has some mass, and it is uniform in density, which means that the center of the board will be the FG for the board. And the scale reads 250 newtons. So in other words, there's 230 newtons of force that's applied up there. And the person here is a distance of 0.5 meters. So in other words, I'm looking at a point of rotation right here, and I'm saying everything needs to be in rotational equilibrium. Okay? So we want to find the weight of the person. So we're looking for his FG. Okay? Now this is of the board. All right. So in other words, I'm going to look at all of the different rotations that could happen, and I'm going to pivot about this point. So in other words, I look at my rotations, and it's going to go around this way. So my FG times 0.5 meters, okay, because that's how far away from the pivot my sumo wrestler is, plus my FG of the board times the halfway of the board has to be balanced. So that's my clockwise rotations. Has to be balanced by my counterclockwise rotations, which is my 230 newtons times the 3 meters. Okay? And so you can actually set this up, and we have all the information necessary to make the FG of the board, because we know that it's 3.4 kilograms and that it's 9.8 meters per second squared, so we can solve that. We actually can solve for this value, and I'm going to leave that for you to do. Okay, so you can kind of check it. The answer, I think, should come out to be like 150 newtons. No, I can't remember. 150 newtons, kilograms, I think. 150 kilograms, if we got to get down to the kilograms. But anyways, it's something that you can solve, and if you have questions, we can deal with those tomorrow. So All right, thanks for watching.